Classifying critical points, part 2, using the first derivative test. So now that we know how to find critical points, we're looking at various ways on how to classify critical points. Sometimes we want to use the first derivative to classify our critical points, and we can do this using the first derivative test. So let's begin by considering the function 4x cubed minus 6x squared minus 72x plus 12. If we take the first derivative of this function, we get 12x squared minus 12x minus 72. Factoring that out, we eventually find that our critical points are x equals 3 and x equals negative 2. So how do we use the first derivative to show if these critical points are local maximums, local minimums, or neither? So it turns out that the critical points divide the domain of f of x into intervals in which the sign of the first derivative remains the same for the duration of that interval. So what does that mean? For example, the function that we have here, the original function, is defined for all values of x. So that means that we are going to divide up the entire interval of the number line, and we're going to divide it at x equals 3 and x equals negative 2. So negative 2 is going to come on the left of the number line to 3. And what's going to happen here is we are going to report what the sign of the first derivative looks like for these three intervals. The intervals are negative infinity to negative 2, from negative 2 to 3, and from 3 to infinity. Because the critical points divide up the domain in this way, things will not change signs between the critical points. We know that at the critical points, the first derivatives equal 0. So that means we need to figure out the sign between these points. So the way we can do this is we can find any number between negative 2 and 3 to test in our first derivative to see if the first derivative is negative or positive. So a number that's between negative 2 and 3 is 0. I can pick any number between negative 2 and 3, but 0 is generally a convenient number to test. So if I put 0 into my first derivative, I'm going to get 0 minus 72. So I get negative 72. That means that all the numbers between negative 2 and positive 3 are going to be negative in the first derivative. So I know that my function is decreasing from negative 2 to 3 in the original function. I also want to know what's happening to the left of negative 2 between negative infinity and negative 2. That's another interval that I see here. So I can pick any number between negative 2 and negative infinity on the number line. Again, I'm going to pick a number that's reasonable to work with, so I'll pick negative 3. If I plug negative 3 into my first derivative, I'm going to crunch that number. Again, I'm plugging it in to my first derivative function, and when I do, I'm going to get positive 72. So since it's positive, that means every single number that I plug into the first derivative between negative 2 and negative infinity, going down to the left, is going to be positive. So that also tells me that my original function is increasing everywhere from negative infinity to negative 2. The last interval that I see here is 3 to positive infinity. So I'm going to pick a number to test between 3 and positive infinity. I'm going to pick 4 because that's an easy one to work with. So I plug 4 into my first derivative. I carefully crunch that number, and I again get 72. So here, because it was positive, I know that all the numbers I could plug in from 3 to infinity will give me a positive result when plugged into the first derivative. So now I have to remember what the first derivative tells me about the original function. If the first derivative is positive, my function is increasing. If my first derivative is negative, my function is decreasing. So let's look at what's happening at x equals negative 2. So at x equals negative 2, f of x is increasing, and then after negative 2, f of x is decreasing. We know from the original function test we looked at earlier that if your function goes from increasing to decreasing, that tells you that your critical point is a local maximum. So x equals negative 2 is a local maximum of f of x. Similarly, if I look at what's happening around 3, To the left of 3, f of x is decreasing because the derivative is negative. After 3, f of x is increasing because the derivative is positive. If your function goes from decreasing to increasing, that means that your critical point is a local minimum. So because we have the relationship between the sign of the first derivative and whether the original function is increasing and decreasing, we get a test for the first derivative that's based on the sign of the first derivative and how it changes around your critical point. So let's see how this rule is written out. Suppose that P is a critical point of f of x. If f prime of x changes from positive to negative around P, then your critical point represents a local maximum. If your first derivative changes from negative to positive around your critical point, then your critical point is a local minimum. And if your derivative does not change signs at all around P, then your critical point is neither a local max or a local min. Remember, this test using the first derivative tells us about local maximums and minimums of the original function. Let's look at some examples. Example 1. So again, we're considering the function 3x squared plus 6x plus 1, and we want to use the first derivative test to classify whether this critical point is going to be a local max, a local min, or neither. So our first derivative was 6x plus 6, and solving for when that equals 0 gave us a critical point of -1. So that means we want to know how our first derivative changes around -1. So we know that at -1, our first derivative is 0. So we want to see what the sign is a little bit to the left of -1 and a little bit to the right. And again, we can pick any number to the left and any number to the right to test within our first derivative, but we want to pick numbers that are easy to work with. So when I pick a number to the right, I'm going to pick 0. 0 is to the right of -1 on the number line. When I plug in a 0, I get 6 times 0 plus 6, which is positive 6. So to the right of -1, I'm positive. When I pick a number a little to the left, I'm going to pick -2. So if I plug -2 into the first derivative, I get 6 times -2 plus 6, which gives me -6. So that means that I'm negative to the left of -1. So here I can see that my first derivative changes from negative to positive around my critical point. So that tells me the original function changed from decreasing to increasing. Both of those things tell me that -1 is going to be a local minimum. So now we've used the first derivative test to classify that critical point. Let's look at another. Example 2. So if f of x is 2x cubed minus 3x squared minus 36x plus 14, we want to use the first derivative test to classify our critical points and determine if they're local maxes, mins, or neither of the original function. So our first derivative is 6x squared minus 6x minus 36. Factoring that out and setting that equal to 0, we get critical points that are -2 and +3. So now we want to determine, are those critical points local maxes, local mins, or neither? So again, I need to consider where these are going to fall on the number line, and then I want to look at the sign of the first derivative around my points. So again, I'm going to pick something a little to the left of -2, something between -2 and 3, and something a little bit bigger than 3. So if I pick something a little to the left of -2, I'm going to start with -3. So I'm going to plug -3 into my first derivative, and when I plug in -3, I'm going to get 36. So here, that's a positive number. So everything to the left of -2 is going to be positive. I'm also going to plug in something between -2 and +3. So the number I'm going to pick here is 0, because 0 is easy to work with. When I plug in a 0, I get -36, which means that that's going to be negative. And then I'm going to pick something a little bit bigger than 3, like 4. And when I plug in a 4, I'm again going to get +36. So here, when I consider -2, I see that my first derivative is going from positive to negative, which means my original function was increasing and then decreasing, which means that -2 is a local max. Similarly, I can do the same analysis for 3. So now I know that to the left I was decreasing, and then after 3 I was increasing. So that means that 3 is a local minimum. So again, the way that the sign of the first derivative changes tells you what the original function is doing, and therefore tells you whether or not your critical point is a local maximum or a local minimum. Let's try some more. Example 3. So for the function x squared over x minus 2, we were able to find the first derivative by using the quotient rule. Simplified, our first derivative was x squared minus 4x divided by x minus 2 all squared. From there, we're able to discern that our critical points are 0, 2, and 4. So now I want to use my first derivative test to determine if those points are local maximums, local minimums, or neither. So again, I'm going to lay out my critical points on a number line. And then I'm going to try to determine the sign of the first derivative for my different intervals here. Here, I have more intervals than the previous problems because I have -infinity to 0, 0 to 2, 2 to 4, and 4 to infinity. Remember, your critical points define your intervals. So I'm going to start off by testing something a little to the left of 0. So I'm going to pick -1 because that feels like it's not too hard to work with. And I'm going to plug that into my derivative function. When I plug -1 in, I'm going to get positive 0.556 rounded. I can round pretty early here because I'm really just concerned with whether the number is positive or negative. So even though the number is really small, it was a small positive number. I'm going to test something between 0 and 2. So I'm going to try 1 here. So if I plug a 1 into the first derivative, I'm going to get -3. So again, I know that everything between 0 and 2 is going to be negative when plugged into the first derivative. I'm going to plug in something between 2 and 4. So between 2 and 4 is 3. So if I plug in a 3, I'm going to get -1. So that's going to be negative. And then finally, I want to plug in something a little bit to the right of 4. So I'm going to plug in 5. So when I plug a 5 into the first derivative, I'm going to get 0.556 again. And again, I'm only concerned with whether it's positive or negative, not how big or small it is. So here I have something positive. So what I notice here is that I change signs at 0 and at 4. However, at 2, to the left of 2, I had a negative derivative, and to the right of 2, I had another negative derivative. So I didn't change signs there. And again, our test tells us that if you don't change signs, then your critical point is neither a local max or a local min. However, at 0, my sign changes from positive to negative as I move from left to right. So that tells me that 0 is a local max. Over at 4, I can see that my derivative changes from negative to positive around 4, and that tells me that 4 is going to be a local minimum. So here, I had a case where I had a local max, a local min, and neither, and I was able to determine that by testing some points around my critical points to see how my derivative changed. Let's look at another. Example 4. Suppose f of x equals x cubed times 1 minus x to the 4th. We want to use the first derivative test to determine if the critical points are local maximums, local minimums, or neither. So finding the critical points depends on first finding the first derivative. So the first derivative, once we've factored it, is x squared times 1 minus x cubed times 3 minus 7x. Setting the first derivative equal to 0 gave us critical points of x equals 0, x equals 1, and x equals 3/7. So again, we want to take our critical points and we want to lay them out on a number line so that we can examine the sign of the first derivative. Now we want to lay them out in order, which means we're going to do 0, and then 3/7, and and then 1, since 3/7 is between 0 and 1. So now I know I want to test some points around these points. So to the left of 0, I'm going to test -1. So if I plug in -1 into my first derivative, I'm going to get 80, which is positive 80. So I know that everything to the left of 0 is going to be positive. Now I want to test something between 0 and 3/7. So I'm going to pick 1/4 because 1/4 is between 0 and 3/7. If you're not sure about a number between a fraction and 0, you can turn that fraction into a decimal to help you pick a number. So when I plug in 1/4 into my derivative, I get 0.032. And again, I'm not so concerned about what the number is, but more concerned about whether it's positive or negative. So that's a positive number. Now I'm going to pick something between 3/7 and 1. So I'm going to pick half. So when I plug half into my first derivative, I'm going to get -0.016. And again, I'm only really concerned about whether it's positive or negative, not how big or small it is in magnitude. So that is negative. Finally, I'm going to plug in something to the right of 1. So I'm going to pick 2 here. And so when I plug a 2 into my first derivative, I'm going to get 44. So again, I can pick anything to the right of 1 I want, and I can use that to figure out what's happening between 1 and infinity. Since 44 is positive, that means the first derivative is positive for everything between 1 and infinity. So one of the first things I notice here is that at 0, my derivative doesn't change signs. It goes from positive to positive, which means that 0 is neither a local max or a local min. At 3/7, my next critical point, I see that my first derivative has gone from positive to negative. If it goes from positive to negative, that tells me that my critical point is a local maximum. At 1, my last critical point here, I see that my derivative has changed from negative to positive. If my derivative changes from negative to positive, that tells me that my critical point is a local minimum. So now I have all my critical points classified. I want to mention here a couple things. First is that if your first derivative is particularly complicated, then this is generally one of the best tests you can use to determine if your critical points are local maximums and local minimums. Other tests, which include the second derivative test, would require taking the second derivative, which can be really complicated in a function like this, or graphing the original function. It's not always easy to graph this type of function, so the first derivative test is really useful here. I also want to point out here that you don't need the actual value of the function here. We can determine if the number is positive or negative by looking at the factored form of each factor. So for example, if I was considering what was happening at 2, I could go to x squared. If I plug in a 2 there, that's going to be positive because anything squared is positive. If I plug in a 2 into the second factor, 1 minus 2 is negative, and a negative number to an odd power is negative. If I were to plug in a 2 into the last factor, I'd have 3 minus 7 times 2. 7 times 2 is bigger than 3, so that's also going to be negative. So I have something positive times something negative times something negative. The negatives would cancel out, and I would get something positive. So without actually calculating the 44, I can use the factors to determine if the result is going to be positive or negative. Let's look at an example of a graph. Example 5. Suppose f prime of x is given in the graph below. Use the graph to determine where f of x has local maximums and or minimums on the given interval. So remember from before, we can find the critical points of our graph, which is the graph of f prime of x, by looking at where our graph crosses the x-axis. That's going to be our critical points. So here we have 3 critical points because again, this is the graph of f prime of x. So again, we can use the first derivative test to determine if these critical points are local maximums or local minimums by looking at how the sign of the first derivative changes. So let's start by considering what's happening at 0, our first critical point. Notice to the left that our graph is positive. It's above the x-axis. But to the right, it's negative. It's below the x-axis. So our first derivative changes from positive to negative. If your first derivative changes from positive to negative, that means that the original function has a local maximum. Our next critical point, which is approximately 3.1, our derivative is negative to the left of 3 and positive to the right of 3. If your critical point changes, if the derivative around your critical point changes from negative to positive, that means that critical point is a local minimum. Finally, our last critical point, which is approximately 6.2, we can see that our derivative is positive to the left and negative to the right. So again, if your derivative changes from positive to negative around a critical point, you have a local maximum. So we are able to determine whether or not these critical points are local maximums and minimums by again looking at how our first derivative changes sign. And as a reminder, the sign of the first derivative on a graph is based on whether the function is above or below the x-axis. Now let's take a look at a table. Example 6. Suppose that f of x and f prime of x are continuous functions that are differentiable. Given the table of values for f prime of x, determine the most likely places that f of x would have local maxima and or minima. We also want to determine what those are going to be. So already, we know that we're going to have a critical point at 6, because at 6, the first derivative equals 0. However, we're also going to have a critical point somewhere between 10 and 12, because our first derivative changes signs. And in order for us to change signs, we have to go through 0. So now we need to determine what kind of critical points these are. So let's start with 6. So at x equals 6, to the left, our derivative is negative, and to the right, our derivative is positive, because it's changing from negative 4 to 5. If your first derivative changes from negative to positive around your critical point, that means that your critical point is a local minimum. Now, let's look at what's happening between 10 and 12. So x between 10 and 12, we can see that the derivative at 10 is positive 2, and the derivative at 12 is negative 1. So therefore, we know that our derivative is changing from positive to negative. Therefore, since your first derivative changed from positive to negative, your critical point between 10 and 12 will be a local max. So you're going to have a local min at 6 and a local max somewhere between 10 and 12. Again, using the first derivative test to classify our critical points.